Hello, I am Shane Brayton Davis Delamore, and this is Code and Optimism, a show where we explore how to solve problems faster with software. Today, we're going to cover the last of the 5 essential elements of good modular software design. It's been a long time coming, and I actually handle quite a bit about this last one, implementation. It's like, certainly implementation matters with your module, but is it like equally important as an essential element as the other ones? And after a bit of reflection and a hemming and hawing, I realized there's something really important about implementation that impacts all the other elements. Let's dive into it. So first of all, continuing our theme of elements, the last element is Earth, and Earth is the foundation of everything, and consequently, it totally makes sense that the implementation is also the foundation of everything. So I think the analogy was pretty good on that one. So why? Why does implementation matter? This is sort of the simple, pithy answer, which is that in order for your module to work well, it has to work well. But let's dive a little bit more into what that actually means. So first of all, there's 2 broad stroke things that good implementation is going to have. One, it needs to be maintainable, which is to say easily refactorable, easily responsive to changes as they come up. And that means high code quality. And we've already discussed code quality quite a bit on this channel. I'll put a couple links in the notes on this. So please dive back into that if you want to think about how do you make your code well maintainable. It also needs to be watertight. And we've talked about this in encapsulation, the importance of watertightness for modules. In fact, that's kind of the cornerstone of what a module is. It's all about isolating a big chunk of code behind a small implementation to give us conceptual leverage. But what does that mean in practice? Watertight is going to mean, roughly speaking, first and foremost, that it is correct. So given the interface as specified, it needs to respond as expected. And it also needs to be performant. So it needs to not be unreasonably slow for requests that seems like they should be not too slow. And it should not be too surprisingly erratic either in the speed at which requests respond. Now you can specify that part of your API is going to have an erratic response, or you can specify that a part's going to be slow. And as long as you specify that, then it's still, I think, we consider to be watertight. But it's these surprising things where it doesn't perform as expected, either in terms of giving you the correct answer or in terms of when it gives you that correct answer, that can break that watertightness. And the last thing is, and it seems a little strange, your implementation should be obscure in a good way. What I mean by that is, as you're making your implementation, you should be thinking in the back of your mind, how can I make this implementation so that even no matter how someone pokes and prods at the interface, it's going to be somewhat difficult to guess at how the implementation works. In the sense that, if there's a clear, obvious algorithm one would use to solve the implementation, like you've got a sort in your implementation. Well, you're going to use an n log n sort, and there's really just a couple options there. And therefore, they can probably guess what sort you're going to be using. It's either be a quick sort or a heap sort or whatever it is from the outside. In fact, some of those they could figure out by doing performance tests, and they could determine based on your average, max, and min runtime of all these different sorts what sort you might be using, right? So they could test your API and determine what you're using for that, and that's okay. But you should try not to have your implementation in some way give itself away. If there are many arbitrary different ways you could solve a problem, you don't want people via the interface to be able to detect which one of the many arbitrary ways. And the reason is because you want to have the flexibility to change to a different arbitrary way if you need to, in response to changing requirements, in response to needing to just work within the implementation to make it work better. You want to have as much flexibility inside the implementation to change things around. And so the only specification you want is what's coming in with the interface. Except, and here's where things are going to get a little more interesting. How does that actually work between the implementation and the interface? So first, is the interface more important than the implementation? In the sense that, does the interface define the implementation? Well, that's generally the first pass how we think about it. The implementation needs to implement what the interface describes. But can an interface specification cover 100% of everything? Well, no, it can't, for the simple reason that 100% truth isn't possible. And we've got an episode back on that, back in the early days of this podcast episode video thing. An interface cannot cover 100%. It can get asymptotically close, but it also gets much more painful as you get closer to those higher percentages. Interface cannot specify everything. And therefore, well, the next question is, then does ultimately the implementation become the ultimate definition? Because in a very real sense, the implementation tells the computer exactly what to do. So it does precisely define exactly what should happen in every possible scenario. It does do that. And again, technically speaking, 100% truth is still not possible. But because there's cosmic rays and other things that will still potentially tweak things. Or, for example, erratic performance, right? So you could have a 100% precisely defined implementation, and it could be very clear what it does. But if you're running on a multitasking CPU that with interrupts and time slicing, then your program could get arbitrarily slowed down in unpredictable ways, and you could therefore have unpredictable performance, even though your code is completely well-defined. So, yes, in reality, the implementation is the ultimate definition of the module's behavior. But there's another problem with this. The problem is that we don't want our implementation to define the behavior from the point of view of the client. We don't want the client to have to think about what's in the implementation. If we're doing that, then we've also lost out on all of our complexity fighting superpowers. We no longer have that leverage, that conceptual leverage of hiding most of the complexity behind a relatively, comparatively simple interface. So, what is the relationship between implementation and interface? And I think this is really the crux of how you need to be thinking about implementation. And that comes down to tests. The reality is you should make the interface cover the right sort of trade-off of definition. It should be as small and as simple and as conceptually easy to think of definition as possible. That gets you to the 80 or maybe 90% point for specifying all behavior. And then you should sort of stop. Because one, if you keep specifying more and more, you're going to make that interface more and more complicated to the point where eventually it'll just be the implementation exposed. You want to make that interface really easy to understand. So you want to do that trade-off, that bang versus buck trade-off of relatively simple explanation, even though it doesn't cover 100% of all the behavior. But before we go to the full spec, straight up to reading the source code for implementation, there is a midway step that actually works pretty well. And that is automated tests. If you write automated tests and they are well done, they themselves can become a fairly readable and authoritative definition of most of the rest of the module's behaviors. The automated tests, particularly in a module that's an API presented to other code, the automated tests should, generally speaking, be testing against the API as if they were an external client. And they should test all the weird edge cases. And they should show what happens with the expected results for all those weird edge cases. Not only will that then become a documentation that then people who want to know more than the spec without having to read all of the source code, they can go and read that. And it's pretty readable usually if you do it well. If you do it from the point of view of, I want someone to be able to read this to understand these nuanced details of the specification. It's also automated testing, which has the huge benefit of, as you change your code, change your implementation, it's going to actually validate that you are still conforming to the spec because you've written the spec as automated tests. So at the end of the day, probably strive for 89% of the interface defining the spec, and then strive for 99% of the spec to be covered in your tests. And that doesn't mean necessarily 99% coverage. It just really means 99% of the ways that end users out in the real world might potentially bump into weird cases. And implementation at the end of the day will be the 100% spec, or really 99 point lots of nines. So now we have this interesting conundrum that the actual full behavior of your module is defined in stages. And sometimes, if you're working with a bigger team, the interface definition might be written by one person or by a group of people that either partially overlap or maybe don't overlap at all with who ends up writing the implementation. So there really needs to be an acknowledgement by the team that whoever's writing the implementation is still going to have some say over what the ultimate spec is. And so if you are involved in the interface spec writing of things, you might want to participate a little bit with the implementation, at least at the test level, and helping define what the test might be. So now, for our final takeaways. First of all, you're going to want to strive for it to be watertight. That's really the key thing we're trying to do across the board here, is trying to hide the implementation away, so it needs to be watertight. You also want to make maintainable for all the reasons why you want good code to be maintainable in general. You want to be able to have it evolve to changing requirements easily and effortlessly with minimal effort whenever you're refactoring your code in whatever way. And the implementation does define the rest of the interface that's not written, the rest of the spec. So the unwritten interface becomes defined in this implementation. But automated tests really are our savior of filling that gap. They can still make something that is reasonably readable by a technical person without having to understand all the nuances of the implementation. So it still gives us conceptual leverage because it's less code to read than the implementation itself. And it is still hiding away the implementation. The implementations can still change more or less arbitrarily without breaking the tests. Again, that is a good designed automated test suite, which ideally acts like a client. And that's how you can make good automated tests that don't break when things change, is that they are defining a good interface so the implementation can still change. So that brings us around full circle to the 5 essential elements: purpose, interface, encapsulation, connection, implementation. And I kind of like using the acronym PI-CI. That's how I've kind of landed on trying to remember it, because CI/CD, something that we say quite often. I like PI, it's cute. But purpose, interface, encapsulation, PI, connection, and implementation, CI. And there's kind of a separation between those. PI is really the core conceptual aspect of a module. That's what is its purpose. That's the biggest concept. Interface is how does that purpose made concrete from the client's perspective. Encapsulation is sort of the understanding how the interface and the implementation have a concrete wall between them. But then connection and implementation are interesting in the sense that they have to do with the fact that every module is just a node in a hierarchy of modules. Every module is built upon smaller modules, and bigger modules are in turn standing on the shoulders of your module. Connection is that acknowledgement that your module exists in a network of pure modules above it within the client, but the implementation itself is also a network of modules interacting with each other. So I hope that all of that helps a little bit with you thinking about modular design. Now, this is all fairly theoretical, as we've been discussing. I think we're probably going to shift gears for the next few episodes to some other topics. There's so much to cover, but I do plan to come back at some future point and actually do a practical exploration of, all right, well, you've got some kind of code. Like, how do you take that code and gradually make it into a module? Like, how does that work in the real world? And how do you do it in an effective way? So that's going to come up in the future. But in the meantime, please, I would love your feedback, your questions, your experiences with making modules and thinking about things as modules. Does purpose, interface, encapsulation, connection, implementation catch the major ways that you think a good module needs to be assembled in order for it to be effective? Did I miss something? Or have you seen other ways of breaking them apart that you think is useful? I originally came up with this whole concept because I wanted to have a good definition that I could pass around to other engineers or to share with non-technical people. And when I started Googling on the internet, I couldn't actually find much out there, which surprised me. So I wrote it up. So once again, thank you so much for spending your valuable time with me. I look forward to discussing this with people. And this is an evolving concept, as all things are. I don't have all the answers, but I think that this helps a lot for me for how I think about modular design. So with that, I will leave you with our reminder that all problems are solvable with enough knowledge.